Hi, everyone, and welcome to this next installment in my Algebra and Precalculus video series. In this video, we're going to continue our discussion on trigonometric functions. We're going to be looking at graphs. We're going to take the same approach that we have previously when we graphed linear functions, quadratic, polynomial functions, exponentials, logarithms. We're going to start by plotting points. Plot enough points, you get a feel for what the picture of this equation should look like. And then we're going to move on to some more sophisticated methods for graphing using graph transformations, again, in exactly the same way that we use them for the non-trigonometric functions. Okay, so we're going to start off. We're going to start off with the graph of the sine function. Now you see the unit circle over here on the left. You see the graph, an empty graph over here on the right. So basically, we're going to start with the unit circle, and that's going to be our tool, our method for generating points. So all the points that we're going to graph, wherever they end up being, are coming from the unit circle. We're not graphing on the unit circle, we're using the unit circle as a way to get our points. All right, so rather than evaluating functions by arithmetic, we're going to evaluate functions, these trigonometric functions, by observation, observing where the terminal point lies on the unit circle. Okay, so again, we're going to start by plotting points. So I'm going to look at multiples of 45 degrees or multiples of pi over 4. Notice on the right-hand side that where I'm going to be graphing over here, the x-axis is labeled in terms of pi. Got negative pi going that way, positive pi is going that way. Right, so I have this set up in the correct window. And the reason my horizontal axis, I'm going to be using 0 to 2 pi, well, because that's one trip in the positive direction around the unit circle. And then once you go from 0 to 2 pi, if you keep going, everything repeats. Right? So the graph is going to basically have one image, one picture, and then it's going to repeat over and over and over again. Right? So we're going to go from 0 to 2 pi, one trip around the unit circle. We're going to end up calling this one period of the function, one period of the function. And then my y-axis, if you notice, goes from -1 or a little beyond -1 to 1. And that's because the unit circle is trapped in between -1 and 1 on the x-axis and -1 to 1 on the y-axis. The graph of the sine function is y values. Right? Y values of the terminal point. So the evaluating the function, this is all things covered previously. Right now, we're going to use our knowledge of evaluating trig functions. All right, so those y values of those terminal points are all trapped from -1 to 1. That's why I have -1 to 1 on the y-axis. Okay, so let's start evaluating. Let's start evaluating some sine functions so we could generate some points. All right, so first angle, 0. That is an angle, puts us right here. All right, that puts us at this. Ooh, let me go back to my. That puts us at this terminal point, 1, 0, and the sine of an angle is the y value of the terminal point. So when the angle is 0, so we're doing angle, and then y value of terminal point. Okay, so these are things we discussed in previously. Now we're putting these into action in terms of graphing. Okay, so when the angle is 0, the terminal point is 1, 0. So the sine of 0 is 0. All right, so that's 1 point on the graph, 0, comma, 0. Right? Each one of these, let me use a different color here. Each one of these is a point on this graph. All right, so our first point is 0, comma, 0. All right, moving on. When the angle is pi over 4, and I'm not using every one of these angles, I'm just going in multiples of pi over 4. But we could use all of them. We could do, it's a little bit more work. We could plot 16 points, but I'm only going to plot 9 points. Okay, so when our angle is pi over 4, that puts us at this terminal point. The sine of pi over 4 is the y value. So that's root 2 over 2. So root 2 over 2 is approximately 0.7. It's about 0.7. So let's put that over here on the side just so we have something to go by. We'll say the square root of 2 over 2 is, it's about 0, just so we know where to put our points. It's about 0.7. Right, so 0.7 is about right there. So this point is right there. When the angle is pi over 4, the function value, when the input is pi over 4, the output or the function value is root 2 over 2, which is about 0.7. All right, so now let's just cycle through our multiples of pi over 4. Right? When the angle is pi over 2, the y value of the terminal point is 1. So pi over 2, comma 1, and there's a point right about there. When the angle is 3 pi over 4, there's our terminal point. Our y value is again root 2 over 2. All right, so we could label these points if we want. That first point was 0, 0. That second point was pi over 4, comma root 2 over 2. Then we had pi over 2, comma 1. Three pi over 4, comma root 2 over 2, right? See, the x value is the angle, the y value is the output of the function, which is the information coming from the terminal point, the y value of the terminal point. Okay, so I think we maybe got the hang of it. So let's pick up the pace. When the angle is pi, the y value is 0. So that puts us back here at the x-axis, the horizontal axis. Next angle I'm using is 5 pi over 4. The sine of 5 pi over 4 is negative root 2 over 2, which is about negative 0.7. It's about negative 0.7. So About right there. Not exactly, but it's, it's close. All right. Next angle. When the angle is 3 pi over 2, we've got a terminal point of 0, -1. So, oh, I think these, hang on. Got to make a couple of changes up here. This should say 3 pi over 2, and this should say 7 pi over 4. My apologies for that. Need to make some edits. Okay, so where were we? When the angle is 3 pi over 2, the point is down here at -1. All right, we got 2 more points to do. When the angle is 7 pi over 4, we've got this terminal point with the y value of -√2 over 2. So we're back to about right there. And then finally, when we are back to where we started, an angle of 2 pi is the same location on the unit circle as an angle of 0. It's the point 1, 0. So the y value of the terminal point is 0. All right, so we could have graphed even more points, right? I used, this was just my choice. I chose to use multiples of 45. So I used all of these angles that I'm highlighting right now. There were 8 more points on the unit circle. I could have plotted 8 additional points. I figured this was enough. 9 points was enough. And so the graph of the sine function is going to be a smooth curve that has a maximum of 1. It comes down. Minimum of -1, right? No sharp corners. It's a smooth, continuous curve. And now what happens if we were to keep going? If we were to keep going around the unit circle for angles larger than 2 pi, we would see this graph do this. Repeat, repeat, repeat. Every trip around the unit circle is one copy of this graph. One copy of this graph that we just generated. All right, so that's the graph of just the sine of x, the sine of x. Now we're going to be graphing more complicated versions of the sine function, but this is our baseline. Okay, I'm also going to talk about the graph of the cosine function. And I'm going to go through that a little bit quicker because it's the exact same process, except these function values came from the y values of each terminal point. For the cosine function, we're going to do the exact same thing, except use the x values. That's it. Use the x values. Our definition of the cosine function uses the x coordinate of the terminal point on the unit circle. Okay. Something looks funny on my graph here. Let me see if I can fix this. All right, that's a little bit better. That's a little bit better. All right, so we can generate the same, by the same process, the graph of the cosine of x by doing the same thing. And I'm going to go through this a little bit quicker because it's just it's a sort of repetition. It's repetitive from the previous slide. So angle of 0, I'll start with an angle of 0. terminal point is 1, 0. So the cosine of 0 is 1. So the cosine graph starts up at 1, whereas the sine graph started down at the origin. All right. I'm going to, again, go in multiples of pi over 4. So I'm going to use all of these angles, multiples of pi over 4. All right. Next angle I'm using is pi over 4, and the cosine is root 2 over 2. So again, it's about 0.7. Right. Next angle, pi over 2. Terminal point is 0, 1. So the x coordinate of that terminal point, or the cosine value, is 0. Next multiple of pi over 4. Oops, let's come over here. 3 pi over 4. The x value is negative root 2. Negative root 2 over 2. And then halfway through the circle, when the angle is pi, the x value is negative 1. Negative 1. Okay, had to make the same adjustment as I did on the previous slide. Again, apologies for that typo. All right, so keeping with the same approach we did for the top half of the circle, let's just keep going. When the angle is 5 pi over 4, the cosine is negative root 2 over 2. About right here. When the angle is 3 pi over 2, the cosine is 0. When the angle is 7 pi over 4, the cosine is root 2 over 2. And when we are back to the starting point, an angle of 2 pi, the cosine is 1. So when the input is 2 pi, the output is 1. All right, so same as with the sine graph, the cosine is smooth, no sharp corners. So it looks like that. And if we keep going again, as with the sine graph, if we keep going, we will get the same image repeated over and over and over. So every stretch of 2 pi, you get one exact copy of this graph. So from 0 to 2 pi, looks like this. From 2 pi to 4 pi, identical copy. From 4 pi to 6 pi, another identical copy, and so on. And also in the negative direction. Every stretch of 2 pi in the domain, you get one full cycle of the graph, one full cycle of the function values. Okay, so we are not going to be graphing just these two, sine x and cosine x. Right, we're going to be graphing some more complicated versions of these functions, and we're going to do them in the same way that we graphed other functions. So in a video, many videos ago, when we talked about graphing things like, I don't know, negative 2x minus 3 squared plus 7, we started with the most basic representative of all quadratic functions. We started with this graph, y equals x squared, which is a parabola centered at the origin. And then we applied these transformations, shifting, stretching, compressing, reflecting. We applied those transformations to that graph. Move it left, right, move it up, down, reflect it over the x-axis, reflect it over the y-axis, stretch it, compress it, all these different transformations. Okay? And so that's how we're going to approach these six graphs. So these are six examples I want to work through in this video, and we're going to do the same thing. We are going to start with the graph of the sine function or the cosine function and then make some changes or transform those graphs. All right. There's a little bit different terminology. So let's go over that first. Shifting the graph left or shifting the graph right. So a horizontal shift. Horizontal shifts are going to be called phase shifts. So the phase shift means horizontal shift for a trig function, right? So just with trig functions, we don't use the word horizontal shift. We call it a phase shift. Vertical shifts are still called vertical shifts. So moving the graph up or down. Reflecting the graph, those are still called reflections. But then the stretching, we have some new terminology down here. So stretching the graph horizontally is going to affect the period of the graph. How fast the graph repeats one full version of itself. Right? One full version of itself. And then the vertical stretching, we're not going to call those vertical stretches. We're going to call those changes to the amplitude of the graph. So we got phase shifts, we got periods, we got amplitudes. So let's see how this all comes into play. So we are going to graph let's see. We're going to graph more complicated versions of y is equal to the sine of x. So if there's a multiple, I didn't mean to do that. I want to do a highlighter here. If there's a multiple out front, that is going to be a change in the amplitude. That's a vertical stretch, same as before. It's always the same. If you have a multiple outside of your function, it's going to multiply all y values or stretch the graph vertically. So we're going to call that amplitude. The next two have to do with stretching. Right? So if there is a multiple in front of the x, so I'm looking down here, horizontal stretch. There's a multiple in front of the x. That changes the period. So it's actually going to compress the graph horizontally. So that's going to change the period. The period of the plain old sine graph, sine of x, is 0 to 2 pi. So the period is 2 pi. So if there's a multiple in front of the x, it's going to change the period by dividing by b, right? Divide all x values by k is what it says down here. Except here I'm using a b instead of a k. All right, and then finally, the phase shift. That's horizontal shifting, right? Horizontal shift comes from addition and subtraction. So there's a little bit of clarification we need here. Because you see right here, if there's a plus c inside the function, you're going to move the graph to the left c units, right? A plus goes in the minus direction, a minus goes in the plus direction, right? But these two numbers are the same. If there's a plus 5, it moves 5 units. But over here, you see not minus c, it's c over b. Now, the reason there's a c over b to do a little bit of factoring, a little bit of algebra. So we could rewrite this. Now, if we factor out that b, we get x plus, factoring means, dividing and multiplying. And so divide on the inside, multiply on the outside, we get c over b. Now, if you were to multiply that back through, like unfactor it, b times x is bx, right? B times c over b would give you the plus c. Right? So this is that horizontal stretch. Right? And this is that shifting the graph horizontally, the horizontal shift. Right, so we don't have to do this. This is just one time, just an explanation of why the phase shift is not minus c, it's minus c over b. All right. So let's see if we could put this into play. So first thing, there isn't always going to be an A, a B, and a C in every problem, where sometimes B is 1 and C is 0. So if let's say B is the number 1 and C is the number 0, then you get y equals A times the sine of x. Right? So all three changes are not going to happen in every single problem. Sometimes they will, sometimes they won't. Right? So let's look at this first problem. The graph of 1/4 sine of x. Now we just graphed the sine of x. Starts at 0, 0, goes up here to about 0.7, goes up to 1, right? So I'm just going to go ahead and draw the graph. Actually, I'll put a red box around this guy. And then I'll put a green box around this guy because I'll graph this one in green. Right, so it looks like there is a change in amplitude. Amplitude is the height of the graph. Right? So instead of going from -1 on the bottom to 1 on the top, this graph is only going to be stuck in here from -1/4 to +1/4. There's no change in the period. The period is 2 pi. Right? There's no change in the phase shift, so the phase shift is 0. And what I like to do is look at the quarter period. Right? So if you think about any sine function, as long as we're not moving it up or down, it goes from 0, then it hits its maximum, then back to 0, then hits the minimum, and then back to 0, right? 0, max, 0, min, 0. And so this is happening at the quarter of the way through the period, multiples of a quarter of the period. So this is a quarter period, go from 0 to the max. This is a quarter period to go from the max back to 0. This is a quarter period, 0 to the minimum. And this is a quarter period from the minimum back to 0, right? Up, back to 0, down, back to 0. Right? So that's how the graph of the sine function is working. So in this one, the quarter period would be pi over 2. So you're breaking the period up into 4 pieces: pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. All right, so what does this graph look like? Let me erase some of this extraneous annotation. And so this graph is going to start at 0, hit its maximum, go back to 0, hit its minimum, and go back to 0. 0 up, 0 down, 0. All right, so the green one is the one we're looking for. 1/4 times the sine of x. All right, so this problem had a change in the amplitude was the only change. Okay, let's start with, or let's do a cosine graph. So notice I've changed the scale on the graph, right, to sort of fit the problem, right? So my y-axis here is going -5 to 5 because I see an I know the amplitude is 4, so I got to go up to +4 and down to -4. So you will have to change how you label the x and the y-axis. And you see my horizontal axis is not going 0 to 2 pi. It's going a little bit past 4 pi. And that's because the problem says make a graph on the interval 0 to 4 pi. All right, so again, I'm going to graph the one we're looking for in green. I'm going to graph the other guy, the plain old cosine graph, in red. So I'll start with that. Cosine graph starts at 1, starts up, goes down to 0, goes down to the minimum, goes back up to 0, and then goes to the maximum. Right? Cosine graph starts up and then does sort of the same thing as the sine graph. I'm going 0 to 4 pi, so let's graph one more period of the cosine graph. Starts up, goes to 0, down to the minimum, which is -1, back to 0, and then up to the maximum. So this is two full periods of the cosine graph. Right? This is one period, 0 to 2 pi. Then it repeats a second period from 2 pi to 4 pi. All right, so now let's look at this guy, the one we want to graph. We want to graph -4 cosine of x. Right? So the amplitude is going to be 4. Basically, how tall is the wave? Amplitude is the absolute value of A. In this case, A is -4. Right? So we're using this model. Y equals A cosine bx plus c. And this problem looks like we've got A is -4 and the amplitude is always positive, the absolute value of that. So the graph is going to start up here at +4. It's going to end at +4, and then it's going to repeat. But then there's that negative sign is a reflection. So it's not actually, so if it was 4 cosine, it would start up. But now to incorporate that negative sign, the graph is actually going to start down. So the cosine graph at each quarter period, so the period is 2 pi, there's no phase shift. The quarter period is pi over 2. So every pi over 2 on the horizontal axis, the cosine graph does one of those important values, one of those important things. So the cosine graph starts at the maximum, then goes to 0, then goes to the minimum, then goes back to 0, then goes to the maximum, right? That's the cosine of x. We're reflecting, we have a negative out front. So all those things are changing. With the negative sign, it starts at the min, then goes to 0. Then it goes up to the maximum, then goes to 0, and then finishes at the minimum. All right, so what does that look like? Starts down here, goes to 0, goes up to the maximum, goes down to 0, and then down to the minimum. So we draw that shape, that wave shape, that smooth, continuous graph, right? And then that's one copy of the cosine graph, one period, and we're just going to draw it again. So something like that. And so again, we're starting with a new graph. We're seeing this red one, the graph of the cosine function or the graph of the sine function. We're starting with a new, baseline graph, basic version, and then we're applying transformations. All right, let's see. We do a few more, start getting the hang of it. All right, so same thing. I'm not gonna do this for every problem, but we'll graph the basic cosine theta. That starts up, goes to 0, down to the minimum, back to 0, to the maximum. So the cosine of theta one period looks like that. I'm switching it up. This is f of theta. The last couple of problems were f of x. We're not, there's no rule that says we have to use x or have to use theta. We can use any variable we want. Right? These are functions. So one period, right? One period of each function. So there's one period of y equals cosine of theta. So now let's look at the other guy. Two times the cosine of 1/3 of theta. Oh, I think let me go back. I wasn't paying attention to my x-axis. I'm sorry. We need to, I was saying 2 pi, but I was drawing it out to 4 pi. So here's 0 to 2 pi. We actually have to squeeze our cosine function in here. It's actually going to look a little more compressed, because here is 2 pi on the x-axis. So there's going to be one period of cosine of theta. Okay, now that that's taken care of. So notice the x-axis is stretched out. It goes up to 7 pi in this case. So we'll talk about y in a moment, but there's going to be a change to the period. So the amplitude is 2. There's a 2 out front. If we go back to the model, y equals a times the cosine of bx plus c. Well, you notice there's a b in this problem. Okay, b is 1/3. B is 1/3. So the period is 2 pi divided by b. The period is 2 pi divided by b. So we got to do 2 pi divided by 1/3, which is the same as 2 pi times 3/1. And 2 pi times 3/1 will give us 6 pi. That means this graph the 2 times the cosine of 1/3 theta, it's going to stretch horizontally. It's not going to go from 0 to 2 pi. It's going to go from 0 to 6 pi. That's why I have, this x-axis already stretched out. Right? So it's going to start up at 2. It's going to end up at 2. And I know it's going to start here and end here. Halfway through, it's going to hit the minimum, which is -2. So the quarter period, we take the period, which is 6 pi, divided by 4, and that simplifies to 3 pi over 2. So every 3 pi over 2, it's either going to be at the maximum, the minimum, or 0. All right, so 3 pi over 2, it's about right there. Right? 3 pi over 2 is 1.5 pi. It's between 1 pi and 2 pi. So there's going to be a point right there. Another point here at 4.5 pi. And here is one period. One period of this guy. F of theta equals 2 times the cosine of 1/3 theta. The 2 stretches vertically. That's a change in amplitude. The 1/3 stretches horizontally. That's a change in the period. And the phase shift, there was no phase shift again. Maybe we'll get to a problem that has a phase shift. We'll see. All right, so here's another one. Graph 2 periods of this function. Now for these last couple of problems, I'm not also graphing the basic y equals sine x or y equals cosine x. We're just going to graph this function. So we've got an amplitude of 6. Amplitude of 6. We've also got a change in the period. There's a b here. The b is pi. The b is pi. So our period. Okay, let's see if we could. It's got to be careful here because it looks like pi's are going to cancel. So now look at my x-axis. I took away the pi's. It's not labeled in multiples of pi. It's back to 1, 2, 3, 4, and so on. So our period is going to be 2 pi divided by b, which in this case is 2 pi divided by pi. 2 pi divided by pi, well, the pi's cancel, and we get 2. So our quarter period is going to be 2 divided by 4, or 0.5. And again, there's no phase shift in this problem. There's no plus or minus in the argument of the sine function. And so going back just to the shape, this is the shape of the graph of the sine function. It starts at 0, goes to the maximum, back to 0, down to the minimum, back to 0. The period is 2, right? So it's going to go, the graph is going to go from 0 to 2. So if it starts at 0, ends at 0, halfway through, it's back to 0. Right? It goes from 0 to the maximum. Maximum is going to be 6. So it's going to go 0, up, 0, down. So down to -6 and then back to 0. But we have a negative sign in front again. So that's going to reflect. That's going to reflect. All the y values that are positive become negative. So this maximum gets reflected down. And this minimum gets reflected up. Right? That's what the negative in front of the 6 is doing. Right, so before we graph our final version, let's put our first point down and our second point up. Because if we take the negative of the max, we get the min. If we take the negative of the min, we get the max. So the graph is going to go down, back to 0, up, back to 0. And that's one period of this graph. Well, the directions say graph 2 periods. So once we do it once, now we repeat. Actually, I like putting those 5 points just as the framework. 0, down, 0, up, back to 0. And so that gives me a framework for drawing a pretty decent version of this graph. All right, so there's 2 periods of the graph. Y equals -6, sine of pi x. All right, so let me just do a couple more, and I want to incorporate some phase shifts, some phase shifting. All right, we've got f of x is equal to -2 times the sine of 2x plus pi over 2. All right, so we got a lot going on here. Right? We've got a change in amplitude. We've got a reflection, a negative sign. That's a vertical reflection. We've got a change in the period. And we've got a phase shift. All right, so let's take care of these things one by one. Let's be systematic. Let's be organized. So our amplitude is going to be 2. Our period is going to be 2. So let me just sort of review all of these, so where these calculations are coming from. And the phase shift is going to be C over B. All right, so we've got y is equal to a, in this case, it's a sine function, so a sine bx plus c. And for this problem, let me go back to green, we've got f of x is equal to -2 sine of 2x plus pi over 2. So a is 2, b is 2, and c is pi over 2. There's the a, the b, and the c. Right? Amplitude is the absolute value of a. All right, actually, let's put a, don't forget the negative sign. A is -2. So the amplitude is the absolute value of a. Absolute value of -2 is 2. The period, we have to take 2 pi and divide it by b. So that's going to be 2 pi divided by 2. 2's cancel. We get a period of pi. Quarter period, divide that by 4. So that's pi over 4. So every pi over 4, the graph is going, the 0 to max, that max to 0, is going, all those changes, right? And now our phase shift, well, C over B. So that's going to be pi over 2. That's C, divided by 2, which is B. So that's going to be pi over 2 times 1/2. Keep change flip. So our phase shift is going to be pi over 4. And I usually like throwing in the negative sign here because we have to, you got to remember that the transformation, the horizontal shift, works in the opposite direction. So I think visually it's helpful if we actually include the negative sign here and say, you could either say negative pi over 4, or you could say pi over 4 to the left, right? But a plus in the function means a shift in the negative direction or to the left. Okay, so that means the starting point, the graph is not going to start at 0, right? Everything is shifted to the left. So the graph is going to start at negative pi over 4. The period is pi. So there's a quarter, there's a quarter, there's a quarter, and there's a quarter. So this is pi. Horizontal distance of pi on the horizontal axis. So the graph is going to start at negative pi over 4, and it's going to end at 3 pi over 4. Right? Once you plot those 5 important points, right? The sine function starts at 0, goes to its maximum, back to 0, down to the minimum, and then back to 0. In this case, there's a negative sign in front of the amplitude. So this gets reflected down and this gets reflected up. Right, so make sure we keep that in mind. Right, the amplitude is 2. So normally the graph would go 0 up, 0 down, and then back to 0. But we have this vertical reflection, so the graph actually starts down, right, and then goes up. Right, so plotting those 5 points, breaking the period up into quarters, right, I think is really helpful. So a negative sine function is going to go 0, down, 0, up, and then back to 0. So we're going to look something like this. All right, one more. We've got a cosine function. All right, y equals a cosine bx plus c. So that's going to be, in this case, 5 cosine 3x minus pi. All right, so let's run through this one. The amplitude is going to be the absolute value of 5, which is 5. The period is going to be 2 pi divided by b, or 2 pi divided by 3. So a quarter of that, divide that by 4. 2 pi over 3 divided by 4 is 2 pi over 3 times 1 over 4, which is 2 pi over 12. And we can reduce that to pi over 6. And then our phase shift. our phase shift is negative C over B. So that's going to be negative of a negative pi, which is pi, divided by B, which is, in this case, 3. Let me put that in green because that's the final phase shift. So we're going to start at pi over 3 to the right. Now, I should have labeled my x-axis in multiples of pi over 6. I have pi over 4s here. So if the graph is starting, right, the phase shift tells you where the graph starts. Starting at pi over 3, so it's going to start somewhere bigger than pi over 4, less than pi over 2. Right? And the period is 2 pi over 3. So if it starts at pi over 3 and then goes another 2 pi over 3, we end up at 3 pi over 3, which is pi. Okay. And I think I should have, this is all kind of issues with how I'm labeling this graph. And this is actually good that this has happened. You have to make sure you're labeling correctly. So I'm going to actually change these into multiples of 2. So let's say 2, 4, 6, -2, -4, and -6, just so our graph fits here. And so our cosine graph starts up, right? So this first point is going to be up here at 5. It's going to end up here at 5. Halfway through, it's going to be down at its minimum. So I'm just sort of loosely estimating where those other points are going to be. So this will be the graph. Now, you just have to sort of visualize this x-axis labeled a little bit differently. But again, I think I'm happy with this sort of this snafu here with the labeling, because it sort of emphasizes what could go wrong when you're labeling the x-axis, the horizontal axis, and the y-axis using a scale that doesn't fit with the, with the actual problem. On my answer key, I'll have it labeled correctly. So when if you look at the worksheet, if you look at the written solutions on this worksheet, you'll see a correctly labeled graph, but it makes things easier when you label the x-axis and you label the y-axis in a way that sort of fits with the problem. Okay, so I'm going to leave it at this. The next video, we're going to continue on with graphing. Okay, but we're going to graph the other 4 trig functions. We'll look at the graph of the tangent, the cotangent, the graphs of the secant, and the cosecant functions. All right, that's it for now. I hope this was helpful.